All right, we are recording. Now I'm going to present my entire screen. All right. If you don't want to have your face shown on the video, keep your monogram up. If you don't mind, it's fine where it's at. All right. So I just closed what I needed actually. All right. So yesterday I got a little flustered and we taught 7-7 to the 6th grade when they were supposed to do 4-7. They did great with it, but we just didn't have homework for it. So it was wonderful. Welcome, Bruce. All right. So we've got everything going. I've kind of got everything I need down here at the bottom. Today's warm-up problems. All right. So with these different things, 3 to the 3rd power means literally, didn't have my pen ready, 3 times 3 times 3, or 27 as they show over here. 4 to the 4th power. All right, we can see that 4 times there. 4 to the 4th power, or 256. B squared, when B is that, that means just put in the 4 for the B, and it's 4 squared, we get 16. All right, N squared times R, well, that means we put in the 3 for N squared, and then for the R, we put in the 2. Now, it's important that we remember, hey, the N and the R were next to each other, right, Lucas? Yeah. So what does that mean when we have two variables right next to each other? Attaboy, that a kid. We're going to multiply them. So we have 3 squared, and then we have 2. Now we know we're going to multiply the 3 by the 2, but we have an exponent. So what do we need to take care of first, Lucas? All right. The 3, like in the 3 to the 2nd power. Oh, gotcha. The exponent. Okay. Yes, because of PEMDAS, parentheses, well, there's nothing happening in these parentheses, so that's all done. Then we have exponents. So exponent 3 squared is 9. Then it'll be 9 times 2. So what does that one end up being, Lucas? So the order of operations is important. Okay. Now, we're going to go all the way back here. We've got this one. Anybody seen Connor yet? No Conrad yet? All right, we're going to get somebody get on his. Okay, you told him, but he didn't get on? All right, well, he's going to have to get a call from Mr. Palm. All right, so, all right, we will call. All right. So if you hear Conrad in the back, that's what it is. All right. So with these guys, the other thing is we had like -6 to the -2nd power. How did we get rid of that negative, crew? That negative in the exponent? Hey, Connor.
Yep.
Are you going to get on math?
Yep. Starting up.
All right, wonderful. We'll look forward to seeing you. We're just doing the warm-ups now. All right, good deal. Okay, crew, are you able to get your mic on? All right, 1 over -6 to the 2nd power. Very good. So anytime we move across, and I'm going to make it a different color here. Anytime we move across this fraction bar, what happens, Tori, to that exponent? Anytime we go across that fraction bar, what happens to that exponent? The exponent there. So it went from top to bottom. What changed about the exponent, Tori? All right, crew, I'll go back to you. Tori may have had a internet issue. What happens to that exponent as we go from top to bottom, crew? Yep, it makes it into its opposite, so it's positive. Okay, so now I have a different question here. Let's see if we can go the other way, Daniel. So what if I have, let's just do 3 to the -2nd, and it's 1 to, How do I get this negative exponent to be positive, Daniel? What do you think I do? You flip it over. So what would that look like? It'd look like 3 to the second. Would that be right? Yes, it would exactly be right. Anytime, anytime, anytime we go across the fraction bar, go above or below it, it changes the sign of the exponent. You wouldn't have to. There's nothing wrong about it. I could do it, and that wouldn't change a thing, Luke or Trenton. The important part when there's a negative sign with it, that's important because this says -6 squared, where this says 3 squared, and even without the parentheses, it said 3 squared. Yep. Great question, though, Trenton. I like it. Now, Haley, I'm coming to you, and it's going to seem like I'm trying to trick you. I'm really not, though, okay? I have 3 to the third power. Hey, everything's positive, everything's good. But could I do this, Haley? Would that be feasible? Oh, do you see how I didn't write the 1? Because do I need to write the 1? No. But do you see how I brought it above? Oh, did I change the sign there? Good job. Good job. Good job. So, anytime we go across that division, the exponent's sign changes, okay? All right, I wanted to hit on that because I wasn't real happy with how I taught that the other day. All right, but today we learn a few more different rules, all right, so that you can go back to, and we're recording, so I'll have that video here. Hopefully it's not too long. So we're going to learn to apply the properties of exponents. Now, if any of you have looked at the homework, there's 3 different things that we're working on today that are there. And we're going to try to cover them all. You may want to get at least 1 or 2 examples of each. Conrad on yet? Anybody see him? Awesome, wonderful. Wonderful. I'm glad to see you, Connor. All right, I'll have to start calling you at 8:05 to make sure all the computer can boot up in that. The factors of a power, such as 7 to the 4th, can be grouped in different ways. Notice the relationship of the exponents in each product. Okay? So, I don't know why we would ever want to do this, but as we look at them, this first one, that's the way we'd normally write it, right? But because we can use associative property, we could look at it like this. Is this technically wrong? No, it's not. This 7 to the third times 7 to the first. Oh, or 7 to the fourth. This will be our first thing that we can notice. We have 7 to the third times 7 to the first. Well, isn't that, let's look back here, see the part that I'm circling? Isn't that just 7 times 7 times 7 times 7? Oh. So does anybody want to take a guess what we do with the exponents when we have 7 to the third times 7 to the first? What did we do with the exponents as we got to the answer? Oh, wonderful. And even if we group them differently down here on the very bottom one, did we add these again, Natalie? Is 7 to the second times 7 to the second? Well, what's 2 plus 2? 4. Oh. So when we multiply numbers that have the same base, we can add the exponents. If they're not the same base, do you think that works? What do you think, Natalie? If it was like 3 times 3 times 2 times 3. Oh, these are all ones, right? So I'm just kind of adding them. So would it be 3 to the second power? Would it be 23 to the second power? Or what would it be, Natalie? Oh, good. So it'd be 2 by itself and 3 to the third power. So if the exponents, or if the bases are not the same, we can't add their exponents. That's what I was kind of going over, and we'll do that. Okay. Here, this is the picture that is in the book. This is the example I like to show out. Oh, 3 to the 5th times 3 to the 8th. Oh, that means 3 to the 5th plus 8. Oh, 3 to the 13th. When, like Haley said it earlier, we are multiplying numbers with exponents, we can add the exponents if the bases are the same. So that might be one you want to take a picture of if you want to kind of go back to it. All right. So like this one, when we look at this one, Trenton, are your bases the same? Yeah, 6 and 6. So what is the answer for this one then, Trenton? If we're multiplying numbers with the same base, what do we do with the exponents? We add them. Okay, so 6 to the 6 to the ninth. 6 to the ninth power. And here's why that makes sense. All right, because, all right, well, they say do this. Well, if I write this one out, wouldn't that be 6 times 6 times 6 times 6 times 6 times 6? Okay, and if I write the 6 to the third out, oh, wouldn't that be another 6, 6, 6? How many sixes did I end up with, Trenton, when I wrote this all the way out? 9. Oh, do you see why we get the 9 now? So if we're multiplying things with the same base, we can just add their exponents, and that's a lot quicker. All right, Michaela, as we look at this one, B, are the bases the same, Michaela? Yes, so what is our answer then, ma'am? All right, if we're multiplying these things, what do we do with the x to the 12th? Nice job, Michaela. N to the 12th. All right, and if I would write n to the 5th out, I'd write n 5 times, right, guys? N to the 7th time, I'd write n 7 times. Oh, that's 12 n's. That's why we can just add those. And yes, ma'am. Okay, thank you for letting me know. I appreciate it, Haley. All right, so n to the 12th. All right, very good. This one right here. Tori, is your mic working yet? Awesome. So what do we do in this situation, Tori? Are the bases the same? The base, yes, okay. What's up here? What exponent is with this second one, though, Tori, since there's nothing written there? Not 0, but 1. Okay? Does that help you out a little bit? Yep. So what's the answer then, madam? Okay. If the bases are the same, what do we do with the exponents, Tori? Yep. So 2 to the 6th. All right. 2 to the 6th. Very good, very good. Remember when. Yes, sir. All right. So you would follow those rules. So if we had something like this, Lucas, is what you're saying? 3 to the negative 4th, all right, times 3 to the 6th, or something like that, right? So now we're looking at these two numbers because the bases are the same. What's negative 4 plus 6? 2. So it'd be 3 to the 2. So we just treat them like we would integers. Does that make sense? Yep, very good question. Very good question. All right. Oh, there's not even any like that on the homework. I thought you were asking because of the homework, but there's not even any like that on the homework. But very good question, Lucas. I like it. All right. So we add exponents here. And anytime there's not a number written for the exponent counter, it is a 1 or anybody else. All right, Christine, as we look at D here, all right, I'm underlining it here. Are their bases the same? Yes. All right, very good, very good. So if we're multiplying and the bases are the same, you just add the exponents. Hey, and we get our answer. All right, Connor and then Summer. Are the bases the same, Connor? So the answer is. So if the bases are the same, what do we do with the exponents, Connor? Okay, so 4 to the 4 to the 6th. All right, very good. Summer, can you see the screen today? Ah, awesome. So you've pinned me up there. Are the bases the same, Summer? All right, so what do we do with the exponents? All right, so x to the fifth power. Wonderful, wonderful, wonderful. All right, so we did really well with that, guys. Now we're looking at these as I go on here. Let's come back to Bruce. Bruce. So as we look at C, x to the fifth, y to the second, are the bases the same, Bruce? No? All right. So if the bases are the same, then what do? Well, if the bases aren't the same, well, then we can just rewrite them like this: x to the fifth, y to the second, and we're good to go. Oh, they cannot be combined. The bases are not the same. All right. So we rewrite them there. Now, this one, Bruce, then, you get a whole page to yourself. Are the bases the same? Yeah, so what is the answer here, Bruce? All right, give me more. It's not just 9. Very good, very good. And guys, you can use that little caret button. It's the shift on 6. So if I would need to do this, I would hit 41. And when I'm typing in the answers, that caret, and then it would be 6. And I'll understand. You guys have all kind of got your own ways, but that'd be a way that make it a lot shorter. If we do 41, do shift, then 6 to get that little caret, this little caret right here, and then the 6, that'll help you maybe shorten putting answers in. All right. So now we need to look at dividing. So if we're going to multiply, we're going to divide as well. And I look right here. I want to write this problem out bigger. So this is maybe an example you would want to write out as well. All right, 6 to the ninth over 6 to the fourth. Now this is where what Lucas asked us is going to kind of come important. Now we can think, if there's one on top and one on bottom, oh, how many 9s would there be on top? Lucas? 9. All right, I'm drawing 9 9s, or 9 6s. All right, how many 6s would there be on the bottom, Gavin? Gavin, did you fall asleep at your computer? Uh-oh, somebody text him and wake him up. Oh, his speaker must not be working today. Is that what he's saying? Okay. So, there would be 4 on the bottom. Do you agree, crew? Yeah. Now, if we were going to reduce, what could we reduce here if we had 6 9s on top and 4 9s on the bottom? Crew, would you still help me out? What could we reduce? Well, could I divide by 6 and 6 on the top and get rid of one pair of 6s? Would that work, crew? And what else could I do, crew? Oh, anytime there's one on the top and on the bottom, we can get rid of them, right? Now, what do we have left on the top then, crew? Oh, 6 to the fifth power. Now, could you write this out every time they give you an equation like this, crew? 6 9s on the top and 4 9s on the bottom, do all the crossing out, and then we get our answer, right? We could do that every time. And if you wanted to, I have no problem with it. But what way did they come up with that was a little bit quicker than that, crew, down here at the bottom? Ooh, do you see how if I take 9, the number on top, and I subtract 4, 9 minus 4 is 5, 6 to the fifth. Do you see how that works? Does that make sense, Lucas? Yes, it does. All right, wonderful. All right. The other thing that we could technically do, couldn't I have 6 to the ninth and, oh, if I want to move this up to the top, oh, couldn't I say 6 times 6 to the negative 4? Then we kind of have a problem that we had before, didn't we? Oh, 9 plus a negative 4. Oh, that is 5. So you can look at it 3 different ways. but I think you guys will get it. So I need to get rid of my writing. Do another problem for you. 5 to the 5th over 5 to the 3rd. All right. When they do that, they write out 5 5s. Do you see that, Michaela? And then 3 5s. And then they're crossing them out because they're kind of canceling things out. They're left with 2 5s on the top. So the answer is 5 to the 2nd power. All right. Let's jump in. Now, with this one, let's go ahead and go to Christine. All right, Christine. So as I look at 7/5 divided by 7/3, what could I do, Christine? Oh, so we could think of it as 5 minus 3. 7 to the 5 minus 3. So the final answer would be. Oh, wonderful job. All right. And the important thing to remember, the number on top always is first and minus the number on the bottom. Now, would it have worked if I would have wrote 1, 2, 3, 4, 5 of these and 3 of those? Do 3 of them cross out then, Christine? Yeah. This is kind of our double check if you're not really catching on to what's going on. Oh, do you see how I have just the 2 left? There we are. Okay, so we're kind of showing you the shortcuts today. Subtract exponents, we get 7 to the 2nd. Now, as we come to this one, is Carson on? Awesome, Carson. All right, wonderful. Glad to see you. What would I do here on B, Carson? X to the 10th minus 9. So what do I get, Carson? X to the 1st. Now, is that an answer right there, Carson? Because it's understood that there's a 1 there, right? Now, could I have wrote 10 x's across the top and 9 x's across the bottom and crossed them all out? Yeah, but it's a lot easier to do the subtraction, right? All right, very good. All right, Summer. 9 to the 2nd over, or excuse me, 9 to the 9th over 9 to the 2nd. What do I do, Summer? All right, so 9 to the 9th minus the 2. I always like to put them up the exponents when I'm drawing. Oh, so we get 9 to the 7th power. Very nice, very nice. All right, feeling pretty good about this. You can go ahead and just tell me the answer here. Let's go to Connor. Go ahead and just tell me the answer here for B, Connor. All right, I like the answer. How did he get to e to the 5th power? What did he do, Michaela? All right, yes, you subtract 5 from 10. Very nice job. Well done. Way to help explain that. Thank you. All right, Connor, you weren't asked to explain it. All right. Now we move on to the next thing, the final thing. So we've had 3 of these pages kind of with this. Let's look here. Okay. So now with this one, this is the one that is a little bit harder. Okay. But I think I can make it make sense. So if we have 9 to the 4th, then do you see how 9 to the 4th is taken to the 5th power? So we have an exponent raised to an exponent. Now, if we really think about that, okay, I'm going to take this right here and I'm going to write it a little bit bigger. Oh my gracious, maybe. All right, we're going to erase everything. 9 to the 4th. And then they said take all that, Trenton, to the 5th power. Okay, so really what they said, and I'm going to change to red, is 9 to the 4th 5 times. So they said 9 to the 4th times 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 9 to the 4th, right? Didn't they say that, Daniel? Yeah, because this 5 said take whatever is inside parentheses and do it 5 times. So we had to take everything inside parentheses, and that included the exponent 4. Well, now, as I look at this, Daniel, oh, I've got all this multiplication. Are all the bases the same, Daniel? So what do I do with the exponents? So it would end up being 9 to the 20th. Oh. So adding 4 5 times, isn't that the kind of the same as, look up here. What did they do in the second step up here, guys? Oh. So I could either write this out 9 to the 4th 5 times and then add them all, or, oh, isn't 4 times 5 20? So good job, Lucas. Good job. I think it was at Michaela there, or maybe it was Natalie. 4 to the 5th power. So an exponent taken to an exponent means we multiply the exponents. Okay? So I'm going to get rid of this so we can read that real quick. Is read as 9 to the 4th to the 5th. Sounds a little weird. Okay? So when we look at these, let's go ahead and go to Trenton. When I look at this one, do we have an exponent taken to an exponent, Trenton? You may still be on mute, but oh, yep. Yes. So what do we do with the exponents now, Trenton? All right, that would work because we could do 5 to the 4th times 5 to the 4th. So what is our answer then, Trenton? So what did we do with the exponents here? 5 to the 8th power. You multiplied it out for us, didn't you? All right, that works good. Now I want to show you one little quick trick there, Trenton. So what you said was exactly right because 5 to the 4th twice. That's what it said. But what is 4 times 2, Trenton? Ooh, do you see the shortcut there? I like what you did, though. I like what you did. All right. I'm glad you did it on the short one, though, instead of the B. All right. And as we go on, Michaela, as I look at 6 to the 7th to the 9th power. All right. Do we have an exponent taken to an exponent, Michaela? Yep. So what do we do, madam? Ooh, 6 to the 7th power. All right. I can do that 9 times. All right. 1, 2, 3, 4. Oh, man. You're making me work now. All right. I think she's happy. She's getting revenge. Mr. Palm's got to work now. All that homework he makes us do. All right. 6 to the 7th. All right. 6 to the 7th. All right. 6 to the 7th. Now that I've written it out all those times, are all these bases the same, Michaela? So what can we do with those 7s? And we get 6 to the 63rd? Yep. Now, what's the shortcut way of doing that, Michaela? Do you remember? Not add, but multiply, because 7 times 9 is 63. Now, what Michaela just did, and this is the greatest reason for doing this right here, writing them all out. She's like, oh, do I add here or do I multiply? Because that's where you're going to find your mistake. When do I add the exponents? When do I subtract them? When do I multiply? And usually the subtract isn't a big problem, but when do I add and when do I multiply? So if you can think like Trenton and Michaela did, oh, this means 5 to the 4th twice. This means 6 to the 7th 9 times. Oh, if you think like that, then you can really quickly understand, oh, I know when to multiply, I know when to add. Okay? So multiply the exponents. Hey, we get 5 to the 8th. Multiply the exponents. Hey, we get 6 to the 63rd. Trenton and Michaela, you did a great job of getting that nailed into us. It was good to have everybody see that again. Now, ooh, here comes one that's not maybe so much fun. 2/3 to the 12th power to the negative third. Oh, what? Yes, sir. Yep. The first section is all multiplying them, so you add the exponents, yes? No, when you're dividing, we didn't do division here. We did exponent to an exponent, we multiply them. Okay? When we divide, we subtract. And we kind of showed you the examples of why that is because, like if I had 12 to the ninth over 12 to the second, there'd be 9 12s on top and 2 12s on bottom. I could cross two of them out, right, Lucas? So that's why I do the subtraction when there's division out there. All right. Very good question. Very good question. All right. And now we kind of move onward and upward to this one that's a pain in the bottom. So with C, I'm not going to have anybody guess. Let's just go ahead and look at C. Okay. Multiply the exponents. 12 times 3 to the negative, or 12 times negative 3. So we get 2/3 to the negative 36th. Okay. So that would be our answer. And if I would look at this, I could go to a lot of trouble to write it out for you. But if we can remember to multiply, hey, we've got our answer. So on this one, let's go ahead and go to Carson. All right, on this one, Carson, D, what would we do? Okay, so I'd get 17 to the negative 40th. So all our rules that we've been working with integers still apply. He's got that same and good answer. Okay, all right, we do that and we get this answer. Now, with this, we could actually think of it as saying, okay, so could I put the 17 to the second over 1? I could. And then I would have 1 over 17 to the second 20 times. Oh. And I could write 17 to the second out 20 times, and 2 plus itself 20 times is 40, right? So this answer is good. Or would this answer be good too, guys? Why is that answer good, Carson? Yep, I did that reciprocal, so it's positive. Anytime, Carson, and that was one thing if you weren't here right at the beginning, anytime we go about across this, it goes from positive to negative. All right. So then we go here. Lucas, do I have an exponent taken to an exponent? We don't? Do I have an exponent taken to another exponent? I do. So what do I do then, Lucas, to get the answer? 3 to the 12th power. Nice. All right. Or if I like really how Michaela and Trenton were saying it, that means 3 to the third times 3 to the third times 3 to the third times 3 to the third. And since Haley, we're multiplying all these, it's the same as adding all their exponents and getting that 12, right? That's why we can take that shortcut. All right, Haley, what's this one? All right, 4 to the 16th power. Or what's the other way of writing it, Christine? Do the long way for me, if you would. Yep, 4 to the 8th power twice. Because that's literally what it's saying. 4 to the 8th power twice. Oh, 8 plus 8 is 16. Or we know 8 times 2 is 16. I'm just doing this multiple times because I found that it helps the students realize, oh, this is why we're doing it. So it was very good that Trenton and Michaela started it off that way. Because I used to not do that, and then people would always get confused. All right. So now when they're negative, all right, we have 1/4 to the 11th to the negative second. What do I do, Summer, when they're negative like this? Is it still the same rules? All right, so what is my answer, Summer? Wonderful, wonderful, wonderful. All right, that's very good. And then what about this one, Tori? D. Okay, so what do I get as my answer then, madam? 13 to the negative 40th power. Okay, because that's saying literally write out 13 to the fourth 10 times. Oh, but on the bottom of the fractions. So it'd be 13 to the fourth times 1 over 13 to the fourth, right? And I could do that 10 times and then I'd add those numbers, right? But I'm going to take Tori's word for it and see that she got the right answer. All right. Very good. Very good. You guys ready to start on this one? Now, I am going to give you work time. I'm going to stop the screencastify right now. I'm going to give you work